So this is actually joint work with my postdoctoral fellow, Jinlong Lei, who's now at Jong-Shi University, and also with two of my collaborators, particularly for part one of this talk, there's Jong-Shi Pang and Suvrajeet Sen. Let me begin. The talk is actually partitioned into three portions. The first part is really an introduction to get people aligned with some of the work that we're doing and provide them with the necessary background. And once we proceed past that, I'll present two of our sets of contributions, particularly best response schemes for stochastic Nash equilibrium problems, and more recently, some of our work that we've been doing on distributed analogs of these schemes, as well as gradient response schemes. So we'll be looking at the n-player Nash equilibrium problem. So these are finite player games, and like the work that Peter was considering and Jerome was considering a little before this. It's a set of n players indexed by I, where the strategy of the ith player is denoted by x sub I, and the strategy set is capital Xi, where capital Xi, we're going to be imposing suitable assumptions subsequently. If I refer to capital X as just the Cartesian product of x sub I, I'm going to refer to the objective of player I, which is by f sub I. And it depends on x sub I and x minus I, where x minus I is just a tuple of rival strategies. Each player is going to be minimizing her own objective given rival actions. So minimize x sub I in capital X sub I of fi of xi given x minus I. Right, and this audience is already fairly knowledgeable in terms of the fundamentals of games. So we're looking for a Nash equilibrium, which satisfies the Nash requirement. And for purposes of this talk, I'm going to be imposing requirements that xi is closed and convex, and fi is convex and xi on an open set containing capital Xi. And the class of non-cooperative games that I'm going to be working with here is going to be referred to as G-script, and it's just a class of static convex games. Okay. And so the first part of the introduction is just going to introduce several types of algorithms, or meta schemes as I call them, and we'll be introducing a layer on top of these schemes. Okay. So one of the simplest known schemes for computing Nash equilibria for these types of convex games is the synchronous gradient response scheme. Okay. So this can be very easily articulated as given a starting point for each player in their individual sets. Every player updates her own strategy by taking a projected gradient step. Right? So it takes its current strategy and moves along the negative gradient by a suitable step length gamma sub ik. And this notation is meant to show that each player can choose her own step length sequence, and this step length sequence could be either diminishing or constant based on whether gamma sub ik is equal to some gamma sub I, right? And you run this for capital K steps, and the choice of capital K is often based on using the rate statements to decide, or if it's in deterministic regimes, you can check in a termination criterion. If it's in stochastic regimes, then these are simulation-based schemes, and you might run this for a fixed number of iterations. But even that fixed number is contingent on an a priori rate analysis, which tells you something about how fast the expected error is diminishing or something of that sort. And I'll revisit this question if I have time. Now, computing a gradient response requires player I to have access to the gradient given x minus I and rival information, right? And so this is something that we're going to be weakening when we move to the distributed regime, but I felt it necessary to point this out, okay? Now, this lends itself to partially distributed implementation, and the term partially here just means that players do need to have access to this rival information for this part, for the first part of the talk. For the latter parts of the talk, and you can see Lachlan did a wonderful job of trying to show how this could actually be learned. In the current setting, or in the third part of this talk, we'll be looking at a subclass of games where this is learned, in fact. Okay. And under some conditions, the synchronous gradient response scheme leads to an any or a Nash equilibrium. Let me just take a slight detour in terms of talking about how one would prove a result like this for folks who are not as familiar with this class of problems. So if I consider a game G that lies in G script, then under the convexity requirements that I've imposed, X star is a Nash equilibrium if and only if X star is a solution to a variational inequality problem X comma F, where X is the Cartesian product and capital F is the concatenated pseudo gradient or gradient map. Okay. And that the variational inequality problem Vi X sub F requires an X such that this inequality holds for all Y. Okay. And here's one such condition. So if F is L Lipschitz and eta strongly monotone, then by picking a gamma that is sufficiently small, the synchronous gradient response scheme converges to the unique Nash equilibrium. Okay, so here's one candidate result. Okay. So here's our first extension to the gradient response scheme. So one of the challenges with having this result is that it requires that the mapping be strongly monotone. Okay. Now, in a lot of cases, you lose strong monotonicity. One such case, for instance, is if you're interested in computing primal dual equilibria where you relax coupling constraints and assuming they're shared constraints, then that game necessarily has a monotone map. Okay. So there's several ways around this, and this talk is not meant to kind of survey those, but here's one result. You can add a regularization. So this is inspired by Tikhonov regularization, and it's actually quite classical. So we call this the iteratively regularized gradient response scheme. And you have, so now instead of one sequence, gamma sub ik, you have two sequences, epsilon ik and gamma sub ik. And if these are both diminishing sequences, and if they are chosen carefully, then synchronous regularized gradient response converges to a least non-Nash equilibrium. Okay, and this allows for merely monotone maps. Now there are other alternatives. One alternative is to use an extra gradient method, but unfortunately that method requires two projection steps. More recently, there's been work done on reflected gradient methods, but again, all of that work can be, I can talk to people about that offline if necessary. Okay. So unfortunately, given the fact that we don't have as much time, it's very hard for me to do a comprehensive review of all literature. So I'm going to be providing at different points a quick survey. Okay. So the earliest work that we know in terms of algorithm design in this context is the work by Tanshu Alpakan and Tamer Bashar. And they had a stream of papers of it. These are just two. Lakra has done some wonderful work in the context of optical networks with Pan and by myself in 2006. And then subsequently, there's been work that we did using iterative regularization, which is the scheme that I discussed on the previous page. And one of the shortcomings of these schemes is that these are not fully rational. So players end up taking essentially what might be viewed as boundedly rational steps. Okay. So here's one avenue that addresses this problem, which is the best response framework. So the best response framework essentially says, instead of taking a gradient response step, each player, given rival strategies, computes what is called the best response, which really requires solving this optimization problem. Okay. Now you can imagine that if f sub I is relatively more challenging to manage, then computing this is not always easy, right? And often if you do work with these, then you need to make properties. So for instance, if you look at what Peter was talking about in this previous talk, there are some assumptions, for instance, that they need to make for the nature of the best response. And I think that's true for a lot of settings that we also have to work. So you have to make some assumptions to get around this. So computing the best response, again, requires player I to know f sub I and x minus I k, but not necessarily f sub j. Okay? Not necessarily, not at all, actually. It again lends itself to partially distributed implementations. But one of the challenges is, in general, of course, this argmin might be multi-valued. And even if it were single valued, it's not even guaranteed that best response schemes necessarily converge to Nash equilibrium. They may lead to cycles. Okay. Here is one resolution to that. Okay, and this is under some conditions. So if you remember in the previous case, we had this argmin where you had fi of xi x minus ik. Under the assumption that f sub I is convex and xi given x minus ik, if you add what is called a proximal term, which essentially is a term which relates xi to x minus ik, which is the previous belief in terms of player I, then this problem is now strongly convex, and this argmin is now a singleton. Okay, and so essentially this is often referred to as the proximal best response. And one of the benefits of the proximal best response scheme is that you can actually, under some conditions on what is called the proximal best response map, you can actually guarantee convergence, and you can actually derive the rate of convergence. Okay? And so this was actually done by Francisco Faquine and Jong-Shi Pang in their book chapter in 2009. And I don't want to spend too much time on it. I just want to kind of remind folks who haven't seen this result. So again, X star is an any or a Nash equilibrium if and only if X star is a fixed point of the proximal best response map. Again, what is the proximal best response map? The proximal best response map takes the previous belief of strategies and computes the argmin for each player, and that essentially captures, you know, the x hat of xk. Okay. Now it turns out that this scheme actually converges linearly when x hat is contracted, and a sufficient condition for that is if you have a suitable spectral property. Okay, now unsurprisingly. Okay. And of course, in this particular case, you actually need fi to not just be C1, you need it to be C2. Okay, so this is one, you know, kind of our basic kind of foundation in deterministic regimes, and I'm going to introduce several extensions to this that we're going to utilize when we look at our stochastic regime. Right. So, and this work is inspired by networked settings where these protocols are being employed for resource management. Okay, and so we're particularly sensitive to the concerns that emerge in networked settings. One particular concern is the way players actually make decisions. So. And so motivated, for instance, by problems in control or / optimization, we consider what is called the randomized proximal best response. So in the randomized proximal best response, what happens is that, so in the synchronous scheme, at every epoch k, every player makes an update. In the randomized regime, what happens is that essentially with probability pi, p sub I, player I makes an update, and with probability 1 minus pi, player I chooses not to update. Okay, so you can see this is again captured here. So you have two qualifiers, randomized and proximal. So the randomized pertains to this specification here, which allows us to decide whether player I should update or not. And the second is, of course, the proximal part, which is this. Okay. So the key difference between the randomized regime, the randomized scheme, and the unrandomized scheme is that exactly some subset of players will end up updating, whilst the remaining subset will not necessarily do so. Okay. So there's, in terms of best response schemes, the literature is a little sparser. The work that we are familiar with, and this goes for everything. So if anyone in the audience or anyone else listening finds that so again, this is a non-exhaustive list, but if someone finds literature that I've missed, which they think might be helpful, please feel free to email me. So there's been a lot of work done by Gesualdo Scutari, Francisco, and Danny Palomar on these types of schemes, synchronous best response schemes. And they've looked at customizing some of these schemes in the context of signal processing, where they actually, in some cases, come up with closed form expressions for these best responses. And that allows you to actually come up with extremely efficient schemes, particularly in these contexts. So now, our focus in this talk is on problems that are complicated by uncertainty. Okay, so we're going to be looking at settings where the objectives are expectation valued, and I might, if time permits, I might talk about risk measures at the end, but it's not clear that I'll get time. But if someone wants to raise that question, I'm happy to kind of talk about it. So you have an expectation over some random integrand, and where psi represents a random variable. And one of the challenges when you're faced with this analog of a non-cooperative game is that a direct extension of gradient response and best response is challenging because you need access either to the gradient of the expectation in closed form, or you need exact solutions to the best response in finite time. And if the expectation is defined over some general measure space, these are generally hard to provide. Okay. Instead, in line with much of the literature on stochastic approximation, and more recently on stochastic first order methods, we assume that there exists a stochastic first order oracle such that it provides a sampled gradient that is both unbiased and has bounded second modes. Now, I should say that more recently we've been able to weaken the unbiasedness assumption and just work with a slightly weaker requirement, but I won't talk about that here. So the unbiasedness assumption can be actually weakened in a regime where you use variance reduction. Okay. But you do require some bounds in the second modes. Okay. Now, just as the variational inequality problem provides a vehicle for succinctly capturing the equilibria of a Nash equilibrium of a non-cooperative game, when clear problems are expectation valued, then the counterpart is a stochastic variational inequality problem, where the term stochastic just pertains to or is meant to note that the components of f are expectation valued. Okay. And so the algorithms for stochastic variational inequality problems, or SVIs, are closely related to schemes for computing Nash equilibrium. So here's one scheme. So if you remember the original synchronous gradient response scheme, we took each player took her previous strategy and then moved along the negative gradient direction using the objective function. Now, instead of using the objective function, you take a sampled gradient. Okay, use a sampled gradient and you just move along a negative direction of the sampled gradient. And under some assumptions on gamma sub ik, you can guarantee convergence. Okay. Now, there's been a host of work both on variational inequality problems as well as stochastic Nash equilibrium problems. And I'm going to, in some sense, put this work together and just do a brief literature review. So the earliest work that we're aware of in the context of variational inequality problems with expectation valued maps is the seminal paper by Haoyang Zhang and Wei-Fu Xu, which was in 2008, where they proved almost sure convergence. Again, using super-martingale convergence theorems. Anatoly Judetsky, Arkady Nemirovsky, and Claire Torvell pursued a different avenue for looking at monotone maps. So they used an extra gradient scheme and used an averaging-based framework to derive rate statements. So rate statements weren't defined here. And so they were able to actually get optimal rates of 1 upon square root k for the gap function for stochastic variational inequality problems. We looked at this problem, the case with strongly monotone maps, and we were able to extend this to the merely monotone regime. And this was joint work with my friend and colleague Angelia Nedic and our doctoral student Jayesh Koshal, by adding a layer of regularization. And so by controlling the rate at which the regularization sequence diminished to 0 and making sure that it aligned with the step length sequences, we were able to contend with merely monotone regimes. But a clear requirement is you need Lipschitzian properties. And this was something that motivated subsequent work with our next doctoral student, where we used random smoothing or convolution-based smoothing. So we used convolution-based smoothing to smooth the objective, and then used that smoothing parameter together with step length sequences to deal with the lack of smoothness. And we were able to also overlay a monotonous, a regularization parameter to deal with the lack of strong monotonous. I should note there's been also recent work on dealing with non-monotone regimes in subclasses of not the most general class, but in various subclasses. So this is wonderful work by Philip Thompson, Alejandro Jofre, and USM, where they actually looked at using a line search and a stochastic regime, which is a very sophisticated analysis. We've been doing some work where we looked at subclasses like pseudo-monotone and certain settings where you have an acute angle property holding, but not the most general class. Okay, not the most general class. So these are all kind of various weakenings of monotonicity, but the most general problem is still a challenging problem. So that brings us to the questions that we're going to be contending with today. I'll be looking at two sets of questions. The first is, how do you deal with, so you can see we talked about gradient response in stochastic regimes, but it's unclear how to deal with best response. And the reason for that is that closed form expressions for the proximal best response map is unavailable in finite time, right? So how do you deal with that? We don't have algorithms for that. And that's what motivated the first work that we're going to be presenting. And we're going to talk about how that can be extended to asynchronous and randomized regimes. The emphasis of the work is really on developing rate statements, complexity guarantees, and addressing questions that have actually already emerged in this very presentation. So I think Peter asked this insightful question early on about what happens when the number of players increases, right? I think this was this question that he asked Lacra, what happens when the number of players increases, and what does that say about the complexity guarantees, right? And we tried to actually answer this question and at least get some handle on what happens. The second part of the talk is going to look at distributed counterparts of both best response and gradient response, where we look at a subclass of games called aggregative games. So this work aligns a bit with the work that Lacra has done, though we look at a more restrictive class of games called aggregative games. Okay. In this case, our goal is really under what conditions on communication and variance reduction can you achieve linear rates of convergence. Okay, so we're trying to see what are the requirements that allow us to recover the fastest possible rates. Okay. Okay, so slightly stricter assumptions for the first part of this talk. I'm going to assume that F is C2 in Xi over an open set containing X sub I, and I'm going to assume that X sub I, capital Xi, is also compact. Okay. If you remember, the proximal best response map now in each player's case looks like this. So instead of F sub I, you have the expectation. Okay. So if you assume that this part is convex, it means the overall part is a strongly convex expectation valued objective. That's still challenging to address, and unless you have extremely strong assumptions, you cannot get a solution to this in finite time. So your only hope is to use an approximation. Okay. So here's one kind of a scheme that this is the first scheme we looked at. So we do exactly what we had said in the synchronous proximal best response scheme with one clear difference. Instead of getting the exact best response, we get what would be the obvious alternative, the inexact variant, where epsilon I sub k plus 1 represents the level of inexactness. Okay, so that's the outer scheme and the outer scheme can be, you can analyze the outer scheme without any consideration of how you compute such a best response, as long as you ensure that this epsilon ik plus 1 goes to 0 at a suitable rate. Okay, so this is just an inexact scheme. It's actually, in our case, happens to be a random variable, and you need some properties in terms of its conditional second moments. But as long as that holds, you can actually go ahead and prove convergence. But from our standpoint, we'd like to make sure that if I tell you that this is an algorithm, for it to be, at least in terms of implementation, you need to be able to tell me how you're going to compute best response step in this inexact form. And the way to do that actually is to use stochastic approximation. Okay, so essentially and that's not the only way. There are, you could use sample average approximation, but we found stochastic approximation to be very useful in this context. So essentially you have the sub problem as a stochastic optimization problem that is strongly convex. What you do is you essentially have a sequence of a set of stochastic gradient steps. But remember, in this particular case, we take a finite but increasing number of stochastic gradient steps. So the algorithm will actually tell you how many steps you need to take instead. How do you know that? Because you have rate guarantees for stochastic approximation. You know that in stochastic approximation, the mean squared error for a strongly convex problem diminishes at the rate of 1 upon k. If you need to make, and based on the rates that you need on this, you can choose what, the number of inner steps you need. Okay. So this is the result I was pointing to. So this is essentially from the seminal volume by Arkady Nemirovsky, Alex Shapiro. I'm sorry. This is not from Arkady Nemirovsky. This reference is off. It's actually Shapiro, Ruzinski, and Dencheva. I apologize. This reference is off. Okay. So essentially what this is saying, this is just giving you the rate of convergence in terms of mean squared error. And what that tells us is that if I want the conditional second moment to be at this rate, that is alpha squared ik. And I'm going to be telling you what I require on alpha squared ik. And that in turn will tell me what j sub ik is. And that will just basically tell me how many inner steps I need. Okay. Okay. So let's just go through the main results for this scheme. So for this scheme, essentially, under the assumption that the proximal best response map is contracted, so that's a key assumption, right? So that would be the counterpart of having the strong monotonicity requirement in the context of gradient response. So you need some sort of contractive property, and that is fairly standard for any kind of best response setting. And if you have that the alpha ik, what is the alpha ik? Alpha ik is this essentially the inexactness sequence. It's the bound on the second moment of the inexactness sequence, which is a random variable. Okay. So as long as that is summable, then you have that the sequence of best response steps essentially converges to the Nash equilibrium almost surely. You also have convergence in mean and convergence of variance of these. So that's not particularly difficult to do. But what is more important is you're actually able to show geometric convergence. So if you remember right at the outset, I said that if you have deterministic proximal best response, you're able to get a linear convergence rate. It turns out here you can also do that. But if you do that, you have to pay the price. And what is the price you pay? The price you pay is essentially the number of gradient steps that you need to do to get a solution. An inexact solution has to grow at a suitable rate, right? So if you're going to require linear convergence, then you know that this inexactness sequence has to diminish at a suitable rate. If it has to diminish at a suitable rate, means that T has to grow at a suitable rate, right? And the goal was to assess what that rate was, okay? And so you're actually able to show that the number of projected gradient steps to achieve an epsilon Nash equilibrium is of the order of square root n over epsilon the whole square, where epsilon is the quality of the Nash equilibrium. And so this goes to Peter's question, what does this say in terms of the number of players, right? So for instance, clearly we at this point, we have a square root n factor which gets scaled by, it's actually n factor on the top. And that's not altogether surprising, but it's something that we were at least able to quantify. But you can see that when you start looking at massive numbers of agents, and this constant is really going to prove debilitating. Okay, I think that's something that we're open about, somewhat depressed about, but that's the reality of it. So, so anyway, so that's the first part, right? So this is the iteration complexity in the case where you have a synchronous scheme. And I want to point out certain aspects of the scheme. So we ran this on a competitive portfolio investment problem. And what we found was that, and this is, I think, around 12 agents, if I'm not mistaken. So if you look at synchronous gradient response, and what we've done is we've compared stochastic gradient with this synchronous algorithm. And what we've done is we've looked at the number of gradient steps required to actually reach within epsilon Nash in an empirical setting, right? Just empirically. And what you find is that while both have, in theory, have the same order, the stochastic gradient scheme requires less, but it requires a lot more communication, right? And the reason for that is every time you take a gradient step, you communicate. On the other hand, when you take a best response step, which actually takes in a lot of inner gradient steps, you end up communicating. So amount of communication requirements for a best response scheme are much, much lower. Now, as a person who doesn't actually work with some of the signal processing and cell phone applications, I'm not as knowledgeable, but in speaking to my collaborators, it turns out that in a lot of settings, communication is actually quite relevant. In cell phone applications where batteries apparently discharge if you communicate too much. So it's a not altogether irrelevant concern. Okay. Let's move on. Let's look at the asynchronous scheme that is also afflicted by delays. Okay. So, and we're looking at settings where players might not be able to make simultaneous updates, nor have access to their rivals' latest information. Okay. So I'm going to assume that at any point I have a player I has access to delayed information. So these are essentially the random variables that specify delay d1 I of k. So it's the delay seen by the ith seen to the ith player by from the first agent at time k. Okay, so these are the delays, and essentially what you have is that these delay random variables are uniformly they're bounded almost surely by some b2, which is some integer, and you also have an integer b1 such that each player updates her decision at least once during a time interval of b sum. And so here's the asynchronous counterpart of the previous scheme. So in the asynchronous counterpart, what you have is essentially that the information that you employ might be afflicted by delays. Okay, and essentially, but otherwise the scheme is essentially what we saw before. Okay, and now once you look at this, the question is again, can you recover the statements that you had before, right? So the statements that you had before were essentially, in the synchronous scheme. So the question is now, when you add asynchronicity and delay, how do the rates change? Okay, so it turns out that you can again show a linear rate of convergence, but what you have is that the constant is afflicted by B1 and B2. Okay, and what are B1 and B2? B1 represents, if you remember, B1 represents the interval over which you have to update at least once, and B2 represents the bound of the delay. So if B2 is large, it means that you can have information which is really quite old. And if B1 is large, it means that players may not update, a particular player may not update for quite a long time. Okay. So, but it turns out that you can actually get a linear rate of convergence, but of course the constants are afflicted by this. And here's what the complexity in terms of projected gradient steps reduces to. I don't want you to get too caught up in the bound, but what I want you to see is how the bound depends on B1 and B2. So the first thing that you notice is that if B1 scales this constant, so if B1 in the best case is 1, because you have to update once every interval. If that happens, you're back to the original world, right? 1 upon epsilon squared. If it worsens, it scales this. So if the exponent was 2, it becomes 2 times B1. Okay. And B2 is the delay. In the best case, B2 is 0. But when B2 is larger than 0, then you have something that shows up in terms of an additive factor. Okay. Here is some schematics that show you what happens. So you still see this linear convergence, but what's happening is that between these, what you're noting is that you're using old information and things are worsening. And then once you actually update, then things start improving, but they can, in the intermediate period, you do have that worsening. So this is from B2 to equals 0 to B2 equals 12. Okay. So in B2 equals 12, you're working with significant delays. B2 equals 0 is the original counterpart. Okay. And you can see the empirical iteration complexity is also afflicted by this. Remember, the iteration complexity affects the constant, right? It affects the constant here. So instead of becoming squared, it becomes 2 times p1, okay? So here's the third scheme. The third scheme uses randomization. So what it says is that, and this is something that was inspired by the randomized block coordinate descent work that has been progressing since the seminal paper by Yuri Nesterov in 2012. It's in the context of block structured optimization, where essentially the coordinates are of a problem are broken into several blocks, and essentially a particular block is chosen to make an update. And so this is, for those of you familiar with these problems, this was, these problems have been considered in the past in a non-randomized setting under the moniker block coordinate descent, okay? Cyclic block coordinate descent, if you will, okay? We were interested in looking at using this notion of randomization in a best response regime when you don't have control over the players. Players are making best response steps without any kind of specification, okay? So this was generalized to the fixed point problem by Convex and Pesquet. And in our focus, what we do is we essentially have a random variable that specifies whether a particular player chooses to make an update or not, okay? And so this was something that you saw already. The key difference, of course, now is that you have randomization and you have inexactness. Okay. And once you have this, again, almost sure convergence are under very similar assumptions and geometric convergence, so you get a linear rate of convergence. The key difference, of course, is that when you look at the rate of convergence, what you find is that the constants are afflicted by the probability that you don't update, or if you will, the probability that you do update. Okay, and so if you find that that this p gets closer and closer to 1, you're going to find that you can recover the statements that you had in the previous case. Okay, so I don't want to spend too much time on this, but you can see, unsurprisingly, that when you have randomization, so the blue here is to represent the randomized regime. The red is well, they're all, I mean, these are just variants across these. Okay. And what you find is that the impact of randomization is on both iteration complexity and linear convergence, and the rate of convergence is just cannot be ignored. Okay. So a quick summary of the results in this part, right? So we had a synchronous algorithm, a randomized algorithm, and asynchronous algorithm. We are able to show almost sure convergence and convergence in mean. And we're able to assess the marginal impacts of both randomization, delay, and asynchronicity on the iteration complexity in terms of inner stochastic gradient steps. Okay, and so and essentially they can be subsumed under this finding. The iteration complexities epsilon's raised to 2 times 1 plus c plus delta, where c is 0 for the synchronous scheme and is positive to capture the cost of randomization and asynchronicity and delay. Okay. Okay, so let's switch gears to the question of computing these equilibria in a distributed regime. Okay, so there's been work right from 2007 where Jason Martin and Jeff Sharma looked at using a game theoretic framework as a means of designing control protocols. Okay, and this has wide applicability since then. And given that our focus is really on trying to compute equilibria of a subclass of non-cooperative games called aggregative games. So these games are essentially games where player objectives are coupled through the aggregate, and this could easily be generalized to a function of the aggregate. And instances of these include the famed Nash-Cournot equilibrium problem. Okay. Again, xi denotes the strategy of player I, while x denotes the strategy profile of the strategy tuple. Player I has an objective fi of xi give an x bar, where x bar is the aggregate. We're going to make assumptions on the convexity of the subproblems as before, and we're going to assume that we have access to a stochastic oracle, okay, and suitable assumptions on the second moments. Okay. So here's a non-exhaustive summary of previous work on consensus and distributed optimization. The earliest work, of course, is the dissertation by John Stiglitz in '84, and there's been a stream of, I mean, this is an extremely well-studied area. Amongst the more storied references, the work by Angelia Nedic and Asuos Daglar in '09 and '10, and there's a lot of work in this area. In the context of distributed schemes for Nash equilibrium problems, Lacra provided some excellent references in the morning. We've done some work in 2016 when we first started looking at these problems. And there's work, of course, by Lacra and her collaborators, Sergio Grammatico and his collaborators, looking particularly at generalized Nash equilibrium problems. Our focus really today is to look at the case that is afflicted by uncertainty. Okay. So I'm going to move a little faster on this because Lacra's already done a fabulous job in terms of providing a survey. In this case, we assume players cannot observe rival strategies, and they interact through a communication graph, which is given as follows. And we're going to assume that essentially, our goal is to design a fully distributed algorithm to compute an any or a Nash equilibrium entirely through local communication and computation. So if you remember in Lacra's presentation, she talked about how certain settings have access to a central coordinator that's able to, in some sense, dispatch maybe dual solutions. We don't have that here. We essentially work with a setting where players, through their own ability to communicate and compute, are able to reach a Nash equilibrium. Okay. But what I want to emphasize here is that my goal really, or our goal really, was to come up with determining how the best known deterministic rates can be achieved. So we know, for instance, if you want to solve, say, a strongly convex optimization problem, the best known rate is a linear rate. The question is, in a regime, or if you give me a Nash equilibrium where the mapping is strongly monotone, that amounts to a linear rate of convergence. The question is, through communication and variance reduction, can I kill both the uncertainty and the consensus error so as to recover this linear rate of convergence? Okay. So if you think about this, where are the two sources of error when you have a stochastic Nash equilibrium problem? Well, the first is that you have noise that comes from the gradient, right? The gradient is noisy. So whenever you probe the oracle, you get a noisy variant of the gradient. The second thing is that you don't have access to the true aggregate, right? So you have some belief. And if that belief is again afflicted by error, then that leads to a propagation of that error. And the question is, how do you develop protocols where you both communicate and kill the noise through variance reduction so as to recover the linear rate, recover a linear rate of convergence, right? And if at all, is that possible? So in this particular case, we're going to talk about both projected gradient response, because this scheme is, there were no results for this, and best response. So we'll start with the projected gradient response. So if you remember the projected gradient response, last time we had just a projected gradient step. Well, now we have two key differences. The first is that every player maintains a copy of the aggregate and essentially uses it to mix uses the beliefs of her neighbors to come up with an improved version or an average version, and uses this aggregate here. Okay, and it doesn't just do this once; it does this tau sub k times. Okay, it does this tau sub k times. Okay, so you have tau sub k communication rounds, and then when you do projected gradient response, you don't just use a sampled gradient, you use S and a sample average using S sub k sampled gradients. Okay. So there are two key changes. This kills the noise. This tau k reduces the consensus error. Okay. Now the question is that together with this, can you actually, so I don't want to spend time on the analysis because I'm running short of time. You can actually show that you can recover a linear rate of convergence in an expected value sense. So now you might find that surprising, right? Because we know for stochastic approximation, the optimal rate is 1 upon k. But remember what I'm doing here. I'm actually using increasing number of samples. And when I do that, this algorithm starts mimicking a deterministic algorithm, which is why you're able to get a linear rate of convergence in the mean. Okay. And what did we need for that? We needed that the number of communication rounds grows at a linear, the linear rate in terms of k, and the number of samples grows at a geometric rate. Okay. Now you might say, well, that seems excessive, and we'll revisit that question. Okay. So if this grows at a linear rate, this grows at a geometric rate, what you're able to show is you get a linear rate of convergence. And the complexity in terms of communication is order log squared. And the oracle complexity, which is the number of gradients that you need over the entire span of the algorithm so as to produce an epsilon Nash equilibrium, is order 1 upon epsilon. Now this matches what you see for stochastic gradient descent, okay? And what we found here is if you look at the number of projections, look, one of the benefits is that when Xi is a very complicated set, then this projection is actually not cheap, right? So you'd like to reduce that. If you use standard projected gradient response, what you'll find is that this becomes the number of gradient steps or projection steps is of the order of 1 upon epsilon. Because we use variance reduction, we can cut that to log 1 upon epsilon. So that's a big step, particularly for computation. Okay. So there's been one other piece of work that we know that where they've increased the amount of communication. There might be other work, but this is the work by Jakotovich, Javier, and Mura. And they're able to show that their communication complexity in the context of distributed optimization is k log k. Okay. Okay, and ours is approximately, is slightly better. Okay. Okay, so now the question I raised was, what happens if probing the oracle is costly? So in a lot of cases, probing the oracle is not cheap. And you can't increase the sampling rate at a geometric rate, right? And so the question is, what happens if you want to work with slower rates? Suppose we work with a polynomial rate, right? So I assume that Sk is k plus 1 raised to v, and tau k is k plus 1 raised to u, okay? Now the question is that what can you get in terms of the rate of convergence? So it turns out you can prove a polynomial rate of convergence, right? Which is governed by the rate at which the sampling rate goes up. And the complexity bounds also, of course, now you lose the linear rate of convergence, so you don't have log 1 upon epsilon. You have 1 upon epsilon raised to 1 upon b. Okay, so you have corresponding degradations in the complexity statements. Okay, but this is important because in some sense, it's important for us to assess how much we can slow down the sampling rate and the communication so as to still get a manageable rate of convergence. Okay. So here are some, so this is for a Nash-Cournot equilibrium problem where we're looking at an Erdős-Rényi graph. And you can see that both, if you compare distributed with centralized, so the blue is is distributed and the red is centralized, you can see some decay in the empirical behavior, but it's not particularly bad. If you compare across graphs, now you remember that the consensus error decays at a geometric rate, but the base for that is beta. And beta corresponds, is derived from the eigenstructure of the graph, right? So if you look at the star graph, that has the best beta, and you can see that shows up in terms of relative error. Okay. Okay. So, and you can see that if and so this is what happens when you compare geometric with polynomial. But I want to just skip ahead and talk about proximal best response. So proximal best response is very similar to proximal gradient response. The key difference is instead of using stochastic approximation to compute the best response, I use what is called sample to best response. So I essentially replace the expectation with a sample average, and I compute a solution to this argument problem directly. Okay, so I'm assuming that somehow I have some optimization software that can contend with this. And there is some hidden complexity here because as Sk grows, computing this is not always easy. That was clean in the previous scheme, right? Because I was directly using stochastic approximation. Here it's not as clean in the sense that here I'm actually assuming that I have a solver that can deal with this as Sk becomes larger. But our goal is to see, well, based on the way Sk grows, what can you say about the complexity and the rate guarantees, right? It turns out that you can get very similar results. And this is quite a busy slide, but what I want to point out is that you get very similar rate guarantees, and complexity guarantees. So this slide actually captures it. Okay, so this is variable sample size proximal gradient response, variable sample size proximal best response. So in all cases, we're able to match the rate. So it's a linear rate for both, okay, which is not surprising. But remember, the requirements are different. Whenever you're working with gradient response, you work with monotonicity properties. When you're working with best response, you're working with the contractive property of the proximal best response map. Okay, but in terms of the results, both the iteration, the oracle complexity, we don't see clear differences in terms of at a higher level. Okay, the constants of course differ. So one thing that I should say is that the behavior of both schemes is similar on a particular set of test problems, but this is something that we're still working on. We're trying to see whether there are settings where we expect best response to behave very differently, and so that's something that's ongoing for us. Okay, so this part we're still kind of playing with a bit. Okay, I have around 7 minutes, so I want to yeah, I want to stop. I'll stop here. So actually we also did some stuff for the non-distributed versions, but I won't present. This is the distributed version. You can see it's very similar. So the communication requirements and the iteration complexities they all match. So I'll stop here and I'll take questions. I don't want to run over. It's 53. So thank you.
Thank you very much for this nice talk. So does somebody have any questions in the chat maybe? Or you can just give your name in the chat if you want to.
Let me see. So should I check to see if there are? No.
I have it under my eye, so
okay.
While people are thinking about the question, I have one for you. Maybe it's a bit naive, or maybe I missed something. So why are you exactly increasing the size of your sampling size? Is it to guarantee the convergence or for the linear rate?
It's for the linear rate. It's for the linear rate. So I can actually, if you use a single sample, you can actually get a lot of this to work. Now, I should say in the distributed regime, so there are 2 or 3 reasons why increasing the sampling size helps. So one is, of course, you can get a linear rate of convergence. In other settings, what we've also found is if you want to weaken the assumption that the oracle provides you with unbiased estimates, you can actually do that by increasing the sample size, because what happens is now the bound on the second moment diminishes at the order of 1 upon sk. So you don't need to kind of deal with the assumption that at every step the first moment is 0, or the conditional first moment of noise is 0. So there are several ancillary benefits of increasing the sample size, but I have to also be honest, there are certain settings where the oracle might be costly to probe, where such an avenue is not advisable, right? I mean, this is in a perfect world where simulation is cheap, right? It works for machine learning problems. It works for problems where it works for some problems. It doesn't work for all problems, because like if your oracle requires you to go and run a queuing simulation, this is a uniquely bad idea.
Yeah. So I think we have Warren also. Yeah, please go ahead.
Hi, let me start by saying thank you for a really fascinating talk. This is not my field of expertise, but I feel a little wiser about it. It was really fascinating to watch the prox show up so quickly. The prox has been showing up in a lot of different applications recently, particularly it's showing up all over the place in machine learning. Right. And one of the reasons is the prox term helps you identify points where the solution is sharp. So it helps you snap to these places where you have sharp solution points. But you've, in yours talk, seemed to assume that all of your functions are smooth. And I was wondering if there's any research or research directions in looking at F being non-smooth and whether the prox is getting the same properties there.
Yeah, that's an excellent question, Warren. So that actually is a fairly simple extension of our work. In fact, in some other work, we already kind of look. It's not difficult for us to kind of adapt that. So since this was the first work in this area, we didn't focus as much on that, but you're right. So let me just point out where. So if you look at, if I go to the first part, right? So if you look at this, and if I, let me show you this part. Yeah. So you look at this part, right? In some sense, I'm assuming that I'm taking the projection on xi. I could take a prox here, and that would subsume this.
Yeah.
Right. So in some sense, then essentially what I'd be working with is that the non-smooth function, if I call it some g sub I, is just the indicator function. So I could work with a host of, proximable functions, if you will. So yes, a lot of this kind of is fairly kind of direct. And so just as whenever you have gradient response, in most cases, if you work with proximal gradient response, everything else works.
Cool. Thanks.
So one thing I should say, the one challenge is if your non-smooth part is also expectation valid. So then you can't take the prox. And one of the challenges when you have non-smooth and expectation valued is something that we've been looking at in separate work on optimization. But that's one instance which people both in machine learning and others have kind of not gone into, because they've been looking at structured non-smoothness.
Yes.
So for unstructured non-smoothness, then you have to use something else, whether it's smoothing or something else, or directly deal with it. Just yeah.
There is some current literature looking at applying proxies to stochastic and expectation objective functions. I haven't seen any of it applied yet.
Yes, there is. There's a fair amount of work where they look at structured problems. So smooth plus non-smooth. So the smooth part is expectation value. The non-smooth part is deterministic.
Right.
So if I can email you offline and point you to stuff where we've been also looking at stuff where the expectation part is also non-smooth, which is quite standard, for instance, when you have risk measures. So when you have risk measures, you often have that you have the non-smoothness showing up as an integrand.
Okay, thank you.
Okay, do we have time for like a super short question or?
Yeah.
Oh, okay, so I just wanted to, I'm sorry if I missed this. It's quite out of my comfort area, but what about Peter's question? What about number of players going to infinity?
Yeah, Peter's question. I'm not, so that just let that one go past me. Yeah. So we do try and, so if you see, we were concerned about that question. So for instance, here, you can see we tried to kind of establish some understanding of how the complexity guarantees are affected by the number of players. But being able to quantify them and being able to is different from saying that it's modest. It isn't modest, right? I mean, you look at this, this is square root 10 already. So, but I don't expect this to be, I mean, think about it. I mean, I don't expect that, because you're looking at a whole set of optimization problems. So I don't expect this to be, I don't have a lower bound on this. So it'd be nice if I had a lower bound to say this is actually optimal. But I think because if you reduce this to optimization, this is optimal.
Right.
Right, but is there a better relationship with the number of players than square root, than n in this case? I don't have an answer, Monica, but I suspect it is. Right.
Thank you.
Okay, perfect. So thank you very much. I think we'll stop here.